The second half of today's presentation will be options for characterizing raw biochar for quality and quantifying properties. This work goes back a very long time. For me, 12 years. I was working for a company that was making biocarbons, and we were looking at how properties of our device were amenable to raw material differences and operating condition differences, and we needed to be able to compare these pyrolyzed materials. So just to let you know who's doing the talking, of these two individuals, the person on the left is Johannes Lehmann, and he is not talking today. The person on the right, the one noted as the undistinguished colleague, is myself, and I will rip through these slides because there's a lot of slides, and I basically captured a lot of information on these slides with the intent being that a person could come back to them and get citations and chase down and drill down into specific issues. So our challenge today is to define these options for characterizing raw biochar for quality and quantifying properties. So I want to immediately pull into reference the IBI standards and the European Biochar Certificate. There's another set of experimental procedures called baseline biochar metrics. They have been developed by myself and some colleagues over the years. And there's a new kit called the Australian Biochar for Soil Standards, which is still being formed. As a point of reference, a standard and a certificate are basically minimum requirements. There's thresholds that must be met to qualify, whereas we are aiming to define analog properties that we can measure and then compare between different materials. So one is a floor that has to be attained. The other is a space above it that relates to properties and perhaps quality. This slide is to capture some references. These are my four favorite places to send people. Warm Heart and Dr. T-Lud are terrific resources. The other two are companies that I'm affiliated with, and they have some references on their websites that you're welcome to refer to. Again, it's more to send you to someplace specific than to just have you Google characterizing biochars, which tends to create an avalanche of relatively uncontrolled quality information. Years ago, there was a book produced called The Biochar Revolution. It's been 10 years since the book came out. It is aged pretty well, but although a lot of work, now we're seeing a lot of research. Back then, it was really a lot of anecdotal advice. And the reason I bring it up is there's a chapter in there called Characterizing Biochars, Attributes, Indicators, and At-Home Tests. And I want to start there because a lot of biochar is made either by home practitioners or developing countries, people that are not going to have access to magic angle NMRs, carbon-13 NMRs, and things like that. So this chapter can be found, I think, by searching out on this phrase, chapter 8, Characterizing Biochars. See what you get. Biochar is a very broad range of properties. Delving into these, I want to start just with the feel of biochar. A good biochar is odor-free, it is not greasy, and we have developed, we stumbled onto a very simple test, which ended up being called the soap test. And that is the concept that if the char is relatively free of greasy mobile matter and tars, then it'll make a dust that just comes off your hands with cold water. And if you need to use soap, then that's called flunking the soap test, and that's not so good. So we had a volunteer years ago at one of our workshops, a week-long workshop, And this is called the soap test. So Amanda, who showed up in the least recommended outfit for working with biochar, which is white, proceeded to get her hands all dirty, and then she rubbed them underneath cold water and observed that the bulk of the dust came off, and as a result, she passed the soap test. Now, it's not fair to look and say, look, there's little bits of charcoal down in my the creases of my hands. It's a qualitative test. It's quick, and frankly, with a load of biochar or charcoal from a fire or something, you can sift through pretty quickly and develop a feel for the greasiness, and if there's any odor, then you have a lot of tars. You have low temperature tars, which are particularly problematic with the sugars leaching. So there are some previous work presentations at conferences. These conferences have been in the United States. They're not accessible to as many people, but here is the preceding work that I've done in this area that will shed more light. A lot of it is reproduced here, but this is, again, for you to find these things, search on that phrase. There was a preceding work called Biochar Standards and Characterization Schemes, how and what is being measured and what it is actually telling you, and it's a more focused comparison of these three options, IBI, EBC, and the baseline biochar metrics, which can be found again by either going to NextChar's website or Dr. Thielud's, or by just Googling baseline biochar metrics. They pop up everywhere on the web these days. And the baseline biochar metrics actually goes back to 2016, and I presented some data there, some earlier work. Most of these, I think, all three of them are just PowerPoint slides, so it's tough because you don't have the explanation. You kind of go from a visual set of data or something, and you don't know how to connect the dots. But these are where the work came from. And the real starting point for all of these is the analogy to coal for charcoal. And we have two basic methods used for coals. One's proximate, where we try to break the material into a fixed carbon, a volatile matter, an ash, and a moisture. And the other is the ultimate, where you start breaking it down into the atomic entities. So let's look a little bit about how these things translate over to biochar and charcoal. There was a pretty aggressive assumption made by IBI that the ASTM tests for charcoal would be appropriate for looking at biochar properties, and I'd like to drill down on that a bit more. From the proximate analysis, we really have four basic groups. They've been renamed, and I'll explain why. Moisture is moisture, and in biochar it comes and goes. Inorganic content is really the ash, and quite often for most biochars made from good clean biomass, these are typically plant nutrients. Mobile matter and resident matter are the two groups we've identified or assigned for the carbon constituents, where the resident matter is going to be the long-term, enduring, doesn't break down in the soil, resistant to microbial degradation, and it provides, it's mostly graphene sheets, and it provides a lot of the unique differentiating properties of a biochar when added to the soil. And one of the most important properties, and I draw your attention to it, is the last one, which is voidage. Biochar is an extremely low density material, and that provides aeration and transfer properties to the soil versus something like a clay, which has a tendency to seal itself off. So in terms of summarizing what these properties relate to, we find that for a biochar, a raw biochar especially, if it's added to a growing system, the ash and the mobile matter are the two that come to the forefront because the ash is typically soluble by and large. And so you get pH effects as this ash dissolves in. You get plant nutrients being added, perhaps phosphorus, not nitrogen. Nitrogen in biochar is generally aromatic nitrogen. It's incorporated into the graphene sheets and is not bioavailable. So whether the label says it has nitrogen, the plant doesn't know that. And if you add 5% nitrogen in your biochar, in a century, you'll have biochar in your soil with 5% nitrogen because it never moved. Mobile matter is important because the mobile matter quite often desorbs into the soil when the biochar is wetted out. And that results in a carbon source. And so the microbes then take the carbon source, they need nitrogen to then grow, and they end up using all the available nitrogen in the soil, and that can be a nitrogen loss to the plants that are growing there. Now, having said that, if you have fairly sterile soil, any life is better than no life. And mobile matter can be a good thing to get the microbiology going, to get a mass of of living tissues and entities and microbiology in the soil. The long-term effect is dominated by the resident matter. That's because the ash and the mobile matter generally are either consumed or wash away in the first couple growing seasons, and the long-term phenomena of biochar addition to soils is associated with properties of the resident matter. We won't really have time in this particular talk to talk about where the cation exchange capacity and the absorption capacity, where they're derived, but they do add significant amounts of both and voidage, porosity, and they're long-term and enduring. So let's start off by imagining our biochar on a weight basis being divided into these 4 constituent groups. We're renaming the volatile matter, we're calling it mobile matter, and the fixed carbon is called resident matter. And why do we do that? Because it's not coal, and we don't want to confuse people, and we want to be working with a unique material. If you drill down a bit, it turns out that each of these groups, so we have the 4 groups, each of those 4 groups actually is made up of 2 or more kinds of material. So in water, we have free water, not free draining water, but water that's held in by capillary forces in the macropores. But then we have bound water, which is either water of hydration to some ash constituent, or it may be absorbed water due to the properties of the biochar. So it's a different class of material, and it leaves under different conditions, generally more aggressive for bound water to exit. Similarly, in the mobile matter components, we have traditional VOCs, solvents, things that can be air sparged out of the they dissolve into water, then they can be removed from that water by air sparging, and then semi-volatile organic compounds. And then resident matter, we have non-volatiles and turbostratic. We'll get to turbostratic in a minute. And then ash, we actually have 2 ash constituents, ash non-volatiles and ash volatiles. Well, I didn't think ash was volatile, but we'll find out. So let's start off by removing the water, and that's because water comes and goes in biochar, and you can add a lot of water to biochar, and until you get it away from there, you don't really know what you're working with, especially on a weight basis. So the problem, of course, is that when you remove water, you also will remove volatile organic compounds that are soluble in that water. It's a partial pressure thing. It's a co-distillation. And we have a problem in that, we're trying to get a split between the water and the mobile matter, and yet as we take water away, we may lose mobile matter. And if we leave water behind, we're likely to think it's mobile matter. So the first issue, of course, is this a desorption or a besorption? And the way you tell them apart is you look at the partial pressure curve. A besorption, it's linear. A desorption, it has these plateaus. And what we see in wood is at low temperatures and low temperature chars, even up to significant surface areas, although meters squared per gram is worthless, another talk. But at higher temperatures, we pick up very characteristic nonlinearity, where the capacity is low, up to about 40% relative humidity. That's the partial pressure there. That's relative humidity. And above 60%, we see the char filling up to close to its capacity, which is quite significant for absorbed water. I mean, 15–20% by weight absorbed water, is a significant amount of water in a biochar. So we know that we have absorption occurring at least in some temperatures ranges. And I want to go look at the IBI versus EBC versus the biochar, baseline biochar metrics. And when we look at them, we see that the EBC and the IBI, they dry at 105-ish degrees C, and the BBM dries at 150 degrees C. And that's because the BBM method adopted the method for activated carbons, because we consider good biochar to have a significant portion of absorption property, absorption capacity, and therefore that absorption capacity is going to handle water vapor just like activated carbon. And when we look at some data that I generated in the lab, we find that we can remove the moisture, frankly, at either 100 degrees C or 150 degrees C, but it can be very, very slow at 100 degrees C. And if you have a lot of moisture, if the biochar is quite wet to begin with, that takes a very long time, and you run a risk of leaching, especially if there's any air circulation in the drying oven. You're going to start leaching the volatiles out. So what we have, and this is an undeniable, unavoidable, live with it situation, is that if you have a char that has a significant amount of mobile matter, especially the VOCs, and it has water you're taking off or driving off with temperature, you're going to have to basically have a compromise, strike a bargain, because any water you leave behind will get counted as mobile matter, and any mobile matter that leaves will get attributed to having been a water. So there's an error there, and that's the nature of this material. It is a complicated material. So here's what we've learned. First off, don't read the protocols. Don't get told to dry for 2 hours at 105 degrees C. Life doesn't work that way. Biochar with the absorbed water can be very difficult, and that's where 150 comes in. Don't go above 200. You're again taking a deeper cut into the VOCs. And it's a balance to be struck. At the end of the day, the BBM gives some very detailed procedures, and we are looking at covering the samples to avoid air stripping and not using circulating ovens. And it just is a way of keeping the errors down, but it doesn't prevent them. Moving on to ash. And I'm moving quickly, but hang in there. You can come back to this and I guess hear the talk at the same time. If anything's going to be well behaved, it's ash. It's conserved under virtually all the conditions of the plant's life and during pyrolysis. And the common consensus is that ash is not volatile nor reactive. So frankly, strategy-wise, remove the water and the organics and weigh what's left and you've got the ash. Well, the common consensus is wrong. Looking at the EBC, the IBI, we have differences. The EBC and the BBM are very similar, and IBI uses the standard test method for chemical analysis, wood charcoal, which is to then remove the volatile matter, then ash at 750 C for 6 hours, which is pretty serious. So let's look at that. The assumption that came out of the literature was that the majority of carbonates, and the issue here is calcium carbonate and magnesium carbonate as an ash constituent, and whether it is stable, and potassium carbonates. And so the statement that appears in the literature, and there is a citation for one of our papers by gurus, Joseph and Lehman, that these resist decomposition at 750 C, which is the temperature we're going to use. So if you're going to make an assumption, a statement, you probably ought to check it in the lab. So I decided, well, if we're worried about calcium carbonate, I went and got some pure calcium carbonate. I happen to have gotten it at some growing show. And I put it into my muffle furnace at 550 and waited, repeatedly for up to 6 hours, and it was stable at 550, bone dry. And then at 650, it started to slowly deteriorate over the next couple hours, and at 750, it dropped to about 60%, which is the loss of all the CO2. So you go from calcium carbonate to calcium oxide. And then worse yet, when you take it back out after it's been converted to calcium oxide, it proceeds to start gaining weight, which is the uptake of either CO2 or H2O from the atmosphere around the lab, and the recreation of calcium carbonate and calcium hydroxide. So we have an analytical nightmare that we have boiled off some of the ash, and then the ash is reverting back to its original form, so the weight is not constant, which makes determining the weight problematic. I tried it also with some samples of what a material we called black, which was biochar, lime, and potassium. And we took all the organics off. We found it was stable at 450 C, stable at room temperature, but if we went to 750, we lost the carbonates. This material had quite a large amount of calcium carbonate in it as the ash constituent. And likewise, upon returning to room temperature, it started changing weight again. So again, it's an analytical disaster. So here's really the problem. Every time you see an arrow, you see a problem. So we have a situation that, depending on the test we're using, we can have ash constituents at 750 breaking down and then getting left, that material that left got attributed to being resident matter, or perhaps being attributed to mobile matter. Or if you don't remove all the, in the ashing procedure, if you don't oxidize all the organics, that material gets counted back as ash. So damned if you do and damned if you don't. So moving quickly along, there's a bit more to cover. Here's what we learned. Don't go to 750 C. Do not use the recommendations of the charcoal proximate analysis. There's some additional things. I have found that using the lids of the crucibles and grinding the material up a little bit helps quite a bit. So these are two materials, left and right. One's been ground before it was ashed. The material on the right ashed a little quicker, but there is still some distributions of the black specks. They can be black metal oxides, but they also might be highly carbonized materials that are just very slow at oxidizing. I think you can look periodically inside the muffle furnace and decide when you're close enough to where you want to be for the ashing test. Lower ash biochars are clearly better. So here's the issues so far that we've come to believe. Drying is a compromise. Ashing should be done at 450 to 550 C, and it's substantially safer to do that. These are the errors that can be incurred from the drying and the ashing step. Lots of arrows, unfortunately. Now let's do quickly mobile matter and resident matter, and then C over C or H over C organic. Basically, the concept is let's heat it up and see what comes off, and we'll call that volatile matter, and whatever stays behind is fixed carbon. That's important if you're burning the coal. It's not important if you're trying to characterize biochar. This is all the various phases that are postulated to exist during the transformation from biomass up to turbostratic material, the stable stuff. I'm not going to dwell on it. It's a complicated thing, but for you scientists out there, it's good stuff to dig into. If we look at the BI standards, we find that there's a heavy reliance for moisture and total ash and volatile matter on this standard test method for chemical analysis of wood charcoal. And I also want to note that the organic carbon has 3 classes, and they are very liberal. You can have, if you have over 10% carbon, you're a biochar in IBI's world, whereas if you're 90% ash, I think you're an ash. Okay, so here's the ASTM protocol. It's fairly specific. I laugh, I've never seen duplicate determinations. But here's really what's important. It's instructing you to take a crucible and sticking it on the door of open the furnace door for a couple minutes and basically partially heat the material. And this is what a muffle furnace looks like at 950 degrees C. So I have found almost never that the actual protocol is followed by a commercial lab or a lab technician, because frankly, it's too dangerous. It's really designed for coal. It's not designed for biochar. We have some precedent in the literature of using lower temperatures and correlating the volatile loss to the volatiles being removed at lower temperatures. In the case of the BVM, we settled on 450, recommendation from Tom Reed. And I think it's as good as any. I'll skip that. There's now an instrument that can do the proximate analysis, but it suffers from the fact that it has a lot of sweep gases. So it tends to strip volatiles off quite aggressively at lower temperatures. Again, this is the kind of data you collect with an instrument where you're getting a lot of data in that you're seeing the temperatures that things are decomposing, what the weight loss is. Keep in mind that as these things are incrementally carbonizing, we are getting volatiles being produced that leave, but some of the material is making more resonant matter. And so we're creating a different biochar as we heat it up. It's less than the original amount, but it is more than the native amount of fixed carbon because you converted the volatile, not the volatile. The mobile matter gets pyrolyzed there. So great, TGAs are the future. When we start going from these mobile matter, resonant matter into H over C organic, we now have to start counting atoms. And counting atoms requires, frankly, instruments, and instruments to require calibrations, and calibrations cost money. But keep in mind, an instrument does what it is designed to do. It goes through the motions. It doesn't interpret. So you have to beware. So this was the amazing data that got produced years ago that suddenly decided that 0.7 of H over C organic was the line in the sand, that above it, it wasn't a biochar, and below it, it was. Frankly, that's not enough data to draw any conclusions in my world. And it is this side of a partitioning, in my opinion. If you read ASTM things closely, you'll find out that they have lots of disclaimers. And so the one under using the ultimate analysis notes that moisture is going to be a problem, and any hydrated moistures in the material are going to show up as hydrogen. So the analysis changes water into hydrogen and counts the hydrogen. Or maybe it's the other way around. In any event, you also got problems that mineral carbonates are there. So if we look closely at the ASTMs, and I'm going to go quickly through these because this is running too long and I want some questions. We find out that IBI and EBC both require you to correct for the CO2 presence, because your instrument is going to take the CO2 off and count it as CO2 and count the carbon in it as CO2. And therefore, you've got to back out the inorganic carbon. And what I found rather irritating is that IBI adopted an inappropriate, there are multiple choices for carbonates, calcium carbonates, and they took the easiest one, which was the one used for marine soils. There's a better one, and I haven't used it either, but I find it irritating to think that IBI would err on the side of convenience. But convenience to them is, I don't know, IBI. Anyways, I want to take a look at what happens if we take some representative numbers and we make these analytical errors and see what it does to the calculated H over C organic. And I'm going to leave these numbers for people to go back in. Basically, if we had a perfect separation, we would remove all the water and no VOCs. If we left the bound water, so I had a material that had you know, a percentage of bound or absorbed water, I left it in. And then the next step, I took off all the VOCs, not the SVOCs. And then the last step, I got real hot and I decomposed the ash. And it creates these different partitionings. And if I go through and then re-agglomerate them or re-aggregate them back into their approximate analysis groups, get rid of the ash, you can see that I'm getting different partitionings. Now the other two for volatile ash, the ash has been removed, but if I look and I calculate up what the H over C organic ratios are, that decomposition of the ash would have produced some C that got counted as CO2. It would produce some CO2 that got counted in the carbon assay. And what we find is our material originally in this example was you know, 0.6. If you screw up the dehydration and the drying, or you leave it out too long and it picks up moisture because it absorbs it, it'll go from 0.6 to 0.7. Bingo, you're no longer a biochar. Or if you make the opposite mistakes and you really drive all the moisture and the VOCs off of it, you can drive your biochar all the way down to the point where it's a higher quality biochar. At this point, I find H over C organic hard to pin my hopes on. So in summary, here's the basic ones. Drying is a compromise. The volatile matter issue really is not correctly dealt with by IBI and EBC. C organic is a tough one because you're really trying to pull out kinds of carbons, and carbons are very much the same. The hydrogen, you get any residual moisture, that hydrogen adds into it. Any carbonates are going to add carbon. So inorganic sources of carbon add as, unless you correctly correct for them. And really H over C organic accumulates all the errors. A very harsh conclusion, virtually all reported biochar characterization data suffers from excessive systematic errors due to IBI protocols. Most errors are easily avoided with proper analytical methods. And the baseline biochar metrics attempt to provide those methods. If you go dig them out, there's a bunch of documents that compare things and discuss them, plus the procedures themselves, and I'm done. So thank you very much for your attention, and I will turn it back to our host and take any questions as time allows.
Thank you very much, Hugh, for your interesting presentation. I know you worked a lot with checking guideline analytical methods. And I certainly agree on a number of them. I'm really interested about the water uptake and the differentiation between at what point you would say that water is part of the biochar you're characterizing. So I mean, you have to differentiate at some point what is part of your of the nature of your biochar and what is adsorbed water or bound water.
Sure. Yeah, you really have three kinds of water. One is free water, where the water is basically surrounded by other water molecules. The second type would be hydrated water, where it's actually part of a mineral complex where you have a certain number of water molecules due to hydration. And they probably are basically part of the structure, and they're probably going to stay that way in the environment of the soil, so they're stable. The middle one is absorbed water, and it's very complicated because above 60% relative humidity, the absorbed water goes to the capacity of the absorption sites. And then below 40% relative humidity, it slowly evaporates back off. And that's because you're at that point where the energy, the heat of absorption matches the entropy loss of coming out of the vapor phase onto the water complex. This is one of the most complicated areas of modeling of carbonaceous materials, but it is well documented and it is real. And it has an effect in the soil of at night, the relative humidity above the soil tends to be greater than 60%, and we find moisture migrating out of the atmosphere into the soil. And then during the day, the soil heats up and it goes below 40%, and it evaporates back off, but it tends to cool the soil. So you have a modulating phenomena, and you have a constant source of 50% relative humidity, moisture, in the non-saturated zones of the soils, which is a very important source of moisture for certain plants and microbes that can then capture that moisture. So it's real, but it's not well understood. And frankly, it's not user-friendly science. It's completely devoid. It's not in the world of soil science. Soil science views water and soil as things filling up capillaries and being squeezed out by various osmotic pressures, and the plant can kind of capture, the plant can capture it if it can suck it out of the pore, but it's below 30, the micropores are too small, etc. An area that needs more research is the dynamics of water vapor in soils, and where how they move around, how plants capture them, how microbes take advantage of them. Does a microbe capture water vapor and deliver that to the plant in exchange for exudates? Again, it's just not science that's been worked out to date.
Thank you. And you got a couple of questions. The first one is from Brian Hughes. More or less. Is very dry biochar a desirable thing? I quench my biochar for safety and dust abatement.
Well, biochar is made very dry because of the temperature, but it's not going to stay dry in the real world. As soon as it hits the air, it's going to start taking up some oxygen and oxides, and it'll release some initial heat, and then the moisture gets absorbed, and then the first time it gets wetted, it gets wetted. So in the course of the life of biochar, it's going to go from 300% moisture relative to its weight to probably 10% moisture, but it's never going to live as very dry, and it'll suck moisture out of anything. When I take biochar out of a pyrolysis furnace, walking across my lab, it is picking up moisture. It is picking up weight. So very dry biochar is an anomaly and not something to be pursued, unless you're shipping a truckload of it, in which case shipping water is less fun.
Then a question to your soap test. Likewise, few Lehman techniques would help the farmers to check their biochar product quality. Is it possible to standardize these techniques to make them, I guess, a little bit like thresholding maybe or something?
Well, yes and no. To be honest, I have found that soil growers have tremendous data acquisition capabilities with tactiles. The feel, the smell, the texture, they can gain a lot. Quantifying it is very difficult from person to person, but it's not difficult within the individual. They will be able to know whether this is better or worse than the other stuff they looked at, and they'll be able to relate whether this property matches the property they're looking for. So I think it's not justified to try to quantify and mechanize a soap test, but I think it is a highly valuable test because it's so simple. And people that work with biochars, that make a lot of different biochars, when they open them up, the first thing they do is they take a smell to see if there's any alcohols or any tarry smells. The next thing is they touch it to see how greasy it feels. So these are very rapid, yet very accurate tests of char qualities, because you'll relate it quickly back to other chars that were good or bad in certain situations. The Australians invariably taste it. And one of my American colleagues insists on that also. To prove that it's good biochar, he proceeds to mash into a mouthful of it. And that's fine as long as you have floss.
Then Previn was asking, the biochar prepared at above 700 degrees can impact the CO2 absorption due to moisture capture.
Yeah, I'm not clear on what he's trying to point at. I mean, at the higher temperatures, what you're going to start to see is you're going to start losing the edge change aliphatics, so your cation exchange capacity will drop down a little bit. You're not really influencing the absorption properties that much, although there is a phenomena where low density chars will start to collapse on themselves, and they'll actually start losing absorption capacity because they actually they absorb onto the two absorbing surfaces, create a single dual layer graphene sheet. And so it's no longer available to take up the water molecules and absorb organics, etc. So yeah, these materials are highly complicated, and every different temperature and every different starting raw material will create a new dynamic for other absorbable things like oxygen, water vapor, CO2, etc.
Okay, if you have questions to Hugh, please.
Oh yeah, I'm easy to find on the web, by the way. If you Google biochar, the word you know how to spell by now, and Hugh, a word you should learn how to spell, or at least you can get it from the first slide, you end up at the stuff I've done, and you'll end up with links to me. I'm at nextchar.com. So happy to answer questions. I'm sliding into retirement, so it's time for me to pass on. You know, as they say, experience is a wonderful thing. It lets you recognize a mistake the second time you make it. So I'm more than happy to share my mistakes with your proposed actions and see if we can't avoid some things.
Okay, thank you very much, Hugh. I would say we are already quite good with the timing. So I would say if there are any more questions you just heard, that you can write Hugh for further questions. And from my side, I would say thank you a lot for your presentation.